Okay, hi everyone again. This is the Algebra in Context presentation, where I'm going to take you through some examples of algebra being used in real life, and then some examples of algebra, particularly with regard to quadratic equations, which is, I'm sure you'll remember, a huge part of GCSE and certainly A level and beyond actually as well. So, what is the point of algebra? Well, to be honest with you, I think that algebra is actually very, very useful for solving just simple problems which are far easier to solve if you write them algebraically than if you try and figure them out with your head. Let me give you a quick example of that. Let's say we have 3 pencils and 4 rubbers, and we know the price is £3.30, but we also know that 5 pencils and 7 rubbers cost £5.70. How much does a pencil cost and how much does a rubber cost? Now, without algebra, I wouldn't have a clue what to do there. Fortunately, I know that this is really just reducible to something else, and I'm just going to let you pause the video if you like. You can try and figure it out for yourself first before I tell you the solution. Okay, I hope you've had a little think about that now. Naturally, this is quite clearly a simultaneous equation. If we write it in terms of, well, P and R, where P is the cost of 1 pencil and R is the cost of 1 rubber, it becomes so much more straightforward. It really does, because we just have 3P plus 4R is 330, 5P plus 7R is 570, and we solve these in the same old way that we solve simultaneous equations. I'm not going to go through a very long explanation of how to do this, because I'm sure you're aware of it. Obviously, I've decided to make the coefficients before P the same, and then I've subtracted, finding that R is 60 and P is 30, so we know the cost of a rubber and a pencil. So that's one example of algebra being used in context. I'd like to quickly show you a couple more now. Here's one I often use, just because I find that the students always want to know how old their teacher is, and so because I'm not really, I don't really care if they find out or not, I often put it in terms of a little riddle, and I say, okay, in 3 years' time, I'll be twice as old as I was 16 years ago. How old am I now? Now, this is probably a little bit easier to do if you just kind of do it by guessing at numbers and eventually finding at one which works. But if you know how to frame it in algebra, it's actually really quite straightforward as well. Once again, pause the video, have a little go at writing it algebraically yourself and solving it. Okay, I hope you had a chance to do that now. So yeah, let's X stand for my current age. If I add 3 to that age, well, that is supposed to be equivalent to, double the age I was 16 years ago. Now actually, I'm going to have to do X minus 16 first there, aren't I? To find my age 16 years ago first, and then double it, and that's why the X minus 16 has gone in brackets. After that, once you've actually modelled the equation, it's very, very straightforward to solve, and you'll see that I'm actually 35. That's one I find works quite well with classes, actually. They're always quite keen to solve that. So as a little starter, if you want to do the same thing, it's very easy to change it so it applies to your own age. Just have a little think about how you want to model the equation, and yeah, that's a nice little starter activity if you've got a lesson on algebra. What I really like to do, though, is a little magic trick. And this one, it doesn't just impress students. I find it can really impress people, people who should know how straightforward this is as well. But so let me do this one. I mean, I normally start by saying, okay, and I've got a class of 30 students. Would you like to see a magic trick? And I'm already handing out whiteboards, the little mini whiteboards which we often use in classrooms, because I find them really quite useful. And then I say, okay, I'm going to try and get you all to write down the same number. I'm going to get everybody to start with a different number, and I'm going to turn it all into the same magic number. And on the face of it, that sounds surely impossible, particularly if I don't know what number they're writing down. It sounds too good to be true, doesn't it? So I ask them all to write down any number they like on their whiteboards from 1 to 10. I tell them, don't show it to me, don't show it to me. Write it down and get ready to do the following operations. Now you can do this in lots of ways, but this is just one way which I've set it up so that I end up with the number 6. You can do it for any number you like. You can get this to turn into any number you like, and you'll see that with the algebra afterwards. But I say, okay, you've all written down a number. I'd like you to add 14 to that number, then I'd like you to double the result, then I'd like you to take 10 away from this. They're obviously doing this, working away on their little whiteboards. then I'd like you to halve the result, and then I'd like you to take away the number you originally wrote down, and finally take away 3. Now, I hope you've tried that yourself with a number, but you should find that you've got 6 sitting in front of you. Now, I don't know, maybe you're impressed, or maybe you're thinking that's an obvious trick. I'm not so sure, but let's have a look at how it works. So yeah, it's really quite straightforward if you think about it algebraically again. First thing I got them to do was add 14, and then I asked them to double it, then I asked them to take away 10, then I asked them to halve it, which is divide by 2, then I asked them to take away the number they started with, and then I asked them to take away 3. Now, I often ask the class, does anybody know how the trick worked? And most of the time someone will say, is it something to do with you getting us to take away the number we started with? And of course it is. That's right. I've tried to hide it as much as I can. You know, I mean, nobody would be impressed if I said, I can turn any number into the number 3, and I'd say, write down a number, okay, add 3 to it, now take away the number you started with, because that would be too obvious. So I've just hidden it in like a forest of algebra, that actual operation. And you'll see that, you know, it easily breaks down all those steps into just equals 6. So it doesn't matter what number they start with, even if they started with 1.987 or 2 pi or 3e squared, they will end up with the number 6 if they repeat that procedure. And that's a nice little thing you can try on younger classes to get them interested in algebra, if you're interested. Anyway, those are just a few quick ideas for how we can make algebra a bit more interesting, a bit more exciting, and a bit more relevant to the average student. Now I want to look at a topic which is vast in its breadth and depth in terms of the GCSE and the A-level, and that is quadratic equations. I'm sure we all remember studying quadratic equations for the first time. So yes, without a doubt, students find quadratic equations and expressions quite difficult. Not impossible though. There are obviously some quite straightforward things that we get them to do, and some more difficult things that we get them to do. It is also quite easy to come up with real life situations whose solution is obtained through solving a quadratic equation. For example, I've got two examples here. The second one a lot more complicated than the first, to be honest, but the first one is a fairly standard one which pops up a lot in GCSE, and that is a picture frame needs to be 3 centimeters wider than its length. If you know the area of the picture is 1120 centimeters squared, find the length and width of the frame. Now we're going to solve that one in a second. The second one I'm going to leave as a little poser for you. In a football league, a grand total of 380 games are played in a season. Given that each team plays everybody else twice, how many teams are in the league? Have a think about that one. If anybody's got a solution for it, I'd love to hear it on the forum, but I strongly believe it will end up with you solving some kind of quadratic equation. So, hopefully the rest of this presentation is simply a reminder for you of all the wonderful things we can ask students to do with a quadratic. So, let's talk about solving quadratics. There's 3 possible methods: factorising, using the quadratic formula, and completing the square. Now, it's well worth remembering that only 2 out of those 3 methods are perfect when a solution exists, of course. Method 1, factorising, it's easy for students to suddenly believe that they can always factorise quadratics, but that isn't the truth, is it? So it's worth pointing that out to them. And out of methods 2 and 3, although they never really like doing completing the square in my experience, I think it's a lovely method, and as I hope you noticed from the link I gave you for the article on 101 uses to a quadratic equation, the quadratic formula is actually derived by completing the square on the general shape of a quadratic equation. In other words, ax squared plus bx plus c equals 0. If you complete the square on that, you will end up with x equals minus b plus or minus so on and so forth, the quadratic formula. So yeah, completing the square is not as useless as it might first appear to students. So, solving by factorising. Okay, I'd like you to give these a try before I'm going to go through it on the next slide. So by all means, once again, please pause the video. It will take you a few minutes, to be honest, certainly for the tougher examples. I've never, and I always am at pains to point this out to students, whilst I expect them to get very quick with the first 3 examples I've given, because you can become very quick at that. The second two examples I've given, I still find that with some of those quadratics, particularly the second one I've given you there, 12x squared minus 14x minus 10 is 0, I still find I have to pause and think with those, and I can easily make mistakes when I'm factorising those. So, have a go at those, and press play in a moment. Okay, here are the solutions. Now I'm sure you remember that the way we factorise quadratic equations is by finding two numbers that add to give the middle term, or the coefficient of x, and multiply to give the term independent of x, the very last term, the number on the end. Of course, that trick only works when you've got 1x squared, or just x squared on its own. So the first three, we could just use that simple approach to factorise it and get it put into brackets. And then we've got x is minus 3 and minus 4 for the first one. We've got x is 32 or minus 35 for the second one, and 7 or minus 3 for the third. Now notice with the second one, what I actually solved there was the picture frame problem. Because as I said, the length could be x, or the width could be x, the length would have been x plus 3, and the area was 1120. Now you might think that it would be very difficult to ask the students to factorise 1120, but I would argue it isn't if you actually do a prime factor decomposition on that number, because what are you going to get? You're going to get 2 to the power 5 times 7, and really the only way you're going to make two numbers which are so close together is by doing 2 to the power 5, which is of course 32, times 5 times 7 is 35. So that gives you your two numbers with a difference of 3. So remember, if you're ever trying to factorise a product, a large number, do a prime factor decomposition on it. It makes things so much easier, it really does. So anyway, I don't think you would have had much trouble with the first three, but let's talk about the last two. Now, why are they more difficult? Well, because it wasn't 1x squared, it was 3x squared for number 4 and 12x squared for number 5. Now, a big question, which I actually didn't realise had a positive answer, is there a systematic approach to factorising those? Now, I was always taught a guessing method. Basically, guess at the numbers which work in the brackets there, and if it works, then you factorised it. You know, if it multiplies up to give what you had originally, you factorised it. If it doesn't, keep guessing. It was only really when I came into teaching that I realised there is actually a systematic approach. Now, I don't like the systematic approach, but I always like to teach the students lots of methods because they like to choose their own methods. Also, I tend to find, and this is obviously a generalisation, but girls seem to prefer a systematic approach to these problems, whereas boys not so much. And as I work in an all-girls school, I always teach the systematic approach now, and I find it goes down very well. So, the systematic approach to factorising a quadratic where a coefficient of x squared isn't 1. Now, I'm showing you this just in case you haven't seen it before. I think it's particularly useful if the coefficient of x squared isn't a prime number. Because if it's not a prime number, then you've got lots and lots of options for what those coefficients going before x in the brackets could be. So, you know, 24x squared plus 29x minus 4, that's a very tricky one to factorise. You could be there a long time trying without the systematic approach. So the systematic approach could make this quicker. So, what we do first is we take the 24 and the minus 4 and we multiply them together, and we make minus 96. Now, that is crucial, and you will always do that as your first step. Take the coefficient of x squared and the term independent of x and multiply them together. Now, it works very similar to what we did before with our quadratics where the coefficient of x squared was 1. Because what you need to do is find two numbers that add to give the middle term still, that add to give 29, but now they multiply to give minus 96. Now, you always need to pause to consider which numbers those are, but if you think about it, that's 32 and minus 3. Now what you can do is rewrite the whole expression, that's 24x squared plus 29x minus 4, and split the middle term up so it's expressed as minus 3x plus 32x. Now I can write that down either way round. I could have had plus 32x minus 3x instead. So now we're left with 24x squared minus 3x plus 32x minus 4. Well, the next step is actually to factorise half the expression, that's the first half, then the other half of the expression, the second half. So what do I mean by that? Well, if you look at 24x squared minus 3x, as you can see, they've got an x in common, and they have the 3 times table in common. So we can take out a factor of 3x out of both of those terms. That gives me a bracket of 8x minus 1 following it, because 3x times 8x would be 24x squared, and 3x times by 1 would be 3x. Likewise, I do the same thing for 32x minus 4. This time all they have in common is the 4 times table, so I take 4 out, and I'm left with a bracket once again, exactly the same bracket, of 8x minus 1. Now that's very important, that, because if they're doing this method correctly, that bracket should be exactly the same in both terms. In fact, it's a very good check for whether you've done the first part correctly, whether you've managed to find the right numbers to split the middle term. So as you can see, we have 8x minus 1. Well, if you think about it, and this was not clear to me initially, but it's very clear to me now, can you see there that we now have two terms? We have 3x times 8x minus 1 in brackets, that's the first term, plus 4 times 8x minus 1 in brackets. Both of those terms have the bracket expression 8x minus 1 in common. So what you can do now is pull the 8x minus 1 out and multiply it by a 3x to give you 3x times 8x minus 1, but also a plus 4. And we're left with the answer fully factorised. I think it's such a clever trick at the end that essentially I'm looking at two terms, both of them have an 8x minus 1 in brackets in common, and therefore I can pull that out and I've fully factorised a quadratic. I really like that method. I was never taught it, or at least maybe I probably was taught it at school, but I certainly don't remember using it after I was taught it at school. I didn't use it at university at all. And when I came back to teach, when I saw that method again, I had kind of like an aha moment where I just realised, so there is a way of doing this without guessing. I hope you enjoyed that, and I hope it was quite useful. Using the quadratic formula. Now, this is quite straightforward because, after all, surely this is just substituting numbers into a formula. How hard can it be? Well, students find it surprisingly difficult once again, and every time, if they make a mistake, they know how to plug numbers into a formula, but when they make a mistake, it's because of the negatives, and also because of the dependency on calculators. Personally, I would avoid using a calculator when you first show it to them, and I would get them to write the answers, as I have done on this slide, in exact form. Now, exact form just means that leave square roots, pies, e's, any other numbers which can be written in exact, as an exact expression. Write down those numbers and leave them like that. It means don't put a decimal approximation. That's what it means, exact form. So if you get them to do this in exact form without a calculator first, they will actually get the right answer. It's when they type it in a calculator, they often type in -3 squared without using any brackets. The calculator naturally squares it and then multiplies it by -1, giving you the answer -9, because the calculator wants it in brackets when it squares it in order to make -3 squared positive 9. So look out for that one. So anyway, if we were given 2x squared minus 3x minus 4 equals 0, all we would need to do is allocate the numbers. 2 will be a, b will be -3, and c will be -4. It has to be in that format. The a has to be the x squared coefficient, the b has to be the x coefficient, the c has to be the term independent of x at the end. Plug it into that formula, which, as you can see, has been graffitied, spray painted, or graffitied onto what looks to me like a bollard at the side of a road. Plug it into that formula, and out pops the answer, really. -3 squared is 9. Careful that you're going to have to obviously add the 32 at the end there, because 4 times 2 times 4 is 32, and that's because you've got -4 times 2 times -4, that becomes plus. Lots of negatives to cope with there, and you'll end up with 3 plus or minus root 41 over 2. Now, just a quick comment at the end to say that calculators will solve these automatically nowadays, or a lot of calculators will. It's worth showing them that, because in the calculator paper they could actually use that to help them get the right answer. I would show them without a calculator first so that they understand it, and then show them how to do it with a calculator so they definitely get it right. Okay, the last thing I want to talk about is completing the square, where we've got x squared minus 8x plus 3, and we've got to write it in the form x minus a squared minus b. That's another way of saying complete the square. Have a go at it first yourself, pause the video, see if you can get the right answer, Okay, I hope you've had a little go. I wonder if you can remember to do this. You may not have remembered how to do this. It's, if you haven't done any maths for a few years, then it's the sort of thing you would forget. All we need to do to complete the square is half the middle term first. Here we've got -8, and so when we halve it, we're going to get -4. Once we've halved the middle term, we now write x minus half that middle term, or if it was positive, x plus, x minus 4 squared in brackets. Now, if you think about what x minus 4 squared actually multiplies out to give, it actually multiplies out to give x squared minus 8x plus 16. If you want to pause the video and check that, please be my guest. But if you do lips and eyes, or if you do my preferred method, which is grid method, you'll see it gives you x squared minus 8x plus 16. And that's why I always take away whatever half the middle term is at the end. So I get x minus 4 squared minus 16, and then I put a plus 3 on the end, because the fact that I've taken away that 16 cancels out the plus 16, meaning that it's exactly the same. Now, if you don't believe me, multiply out my final answer, which is x minus 4 squared minus 13, right now, and you will see that after you've simplified the terms, you get x squared minus 8x plus 3. So completing the square isn't too difficult, really. It's more awkward when the coefficient of x squared isn't 1, but they only have to do that at A level, so I'm going to leave that for this presentation. I'm now going to talk to you about why we bother completing the square. And the answer is, firstly, we can use it to solve equations. So let's use it to solve x squared minus 8x plus 3 equals 0. Now, I would argue that this is easier than using the quadratic formula, and it gives us an exact answer. All we have to do is write it in completed square form. Now, we've already done this one on the last slide, and as we know, it comes to x minus 4 squared minus 13 equals 0. Now add the 13 and square root it, so we know what x minus 4 equals. It's plus or minus root 13. Don't forget the plus or minus, because when we square root a number, there are two answers. And then add across the 4. So x is 4 plus or minus root 13. Those are the solutions, or the roots of the equation. When you see that word, the roots of the equation, it simply means the solutions of the equation. Okay, that's one reason we use completing the square. The other reason we use it is to find the minimum or maximum vertex. If you've got x squared minus 8x plus 3 equals y, and you want to find the minimum vertex, the easiest way to do that is to complete the square on it. So we have y equals x minus 4 squared minus 13. Then you can immediately see that the minimum vertex, which is where y is minimized, is going to occur at negative 13. That's the y value, not the x value. The reason why y cannot be any smaller than negative 13, i.e. a minimum there, is because the first part of our equation is stuff squared. It's x minus 4 squared, or stuff squared as I would call it. Well, when you square something, the answer is always 0 or bigger. And if we're trying to make this as small as possible, we'll want that to be 0. And when that something in the brackets squared is 0, y will be minus 13. Well, x will have to be 4 in order to make that bracket 0, and therefore y is minimized when x is 4 and y is minus 13. I like completing square because it's quite logical. The last thing I'd say about completing the square, and I hope you picked this up from the website article on 101 uses of quadratic, that article actually shows you that you can use completing the square to deduce the quadratic formula. That quadratic formula wasn't pulled from thin air. We simply completed the square on ax squared plus bx plus c equals 0. Now, I probably wouldn't show them that at GCSE. Depends, if I've got a very bright set, I might do. But I would definitely show them that at A level, because I think it's important that they understand where these formulas come from. Okay, so let's just have one last little look at what those two things have done. If you look at the graph of y equals x squared minus 8x plus 3, well, when we solved that equation, we found the x values for which the graph crosses the x-axis. They are 4 minus root 3 and 4 plus root 3, because y would be 0 anywhere on the x-axis, and we solved 0 equals x squared minus 8x plus 3. Hence we found the x-coordinates where y is 0, and they are 4 minus root 3 and 4 plus root 3. We also found a minimum vertex. That was found by completing the square, and as you can see on this graph, certainly its minimum vertex occurs when x is 4 and y is minus 13. Lastly, we can find the y-intercept, because for any polynomial, that includes whether it's a linear equation in the form y equals mx plus c, whether it's quadratic, whether it's cubic, if it's multiplied out like that, the final number on the end, the term independent of x, well, that will be our y-intercept, because sure enough, if x is 0, y equals 3, and that's why it crosses at the coordinate 0, 3. Okay, I hope that was useful. I hope it was just a bit of a reminder for you really of some of the things you might have looked at GCSE and A level. I hope you enjoyed the presentation. Please don't hesitate to email me if there's anything you're confused about, if there's anything I can clarify. Okay, thank you very much. Bye bye.